Here in 16.2, we're going to look at how to actually run the mobile manipulation. We'll start with a simple example and then do something more advanced later. We're going to have this basic scenario, the Baxter on the mobile base, with the Kinect, 2 arms, and the idea of picking and dropping off blocks. And our last chapter, we introduced the coordinator package. And here, in addition to the coordinator package, we're going to be working with a navigation, action server, and client that are using move base goal action messages to communicate with the navigation system. And then after that, we have the same setup that we had from last time in the coordinator package, where the task action client has all the interfaces to actually acquire the block. So you can ask the server to move the arms to a pre-pose position. You can ask the visual service to find the table, find the block, and then return the pose of that block. We're able to ask the planning and execution of the manipulation segment to pick a block or drop it off. Okay, so this is the kind of interface that we're working, and the navigation part, of course, is what's new here. Now let me give you an overview of what we're going to be trying to do in this demonstration. Number one, we're going to grab a block from the first table. Actually, let me show you the diagram. So the first table is located over here, and the robot will start right next to it. So the first thing we want to do is grab that block. Then we're going to want to move the robot back a little bit just to avoid a fatal mode in navigation. That can happen anytime you're very close to an environmental object, because it means that you may have a collision. So as part of the SLAM algorithm, you have some parameters that indicate that we should not come within a certain distance of the environment to avoid a collision. But if you start that close to another object, you might find yourself in a fatal mode. So what we want to do is, before starting navigation, we're going to move manually with some service calls so that the robot is out here. After that, we want to do autonomous navigation. First, we're going to use something we call a waypoint or a via point and place it around here just to get the robot started and getting over here around this open alleyway. And then after that, we're going to send it over here to the table. Now, initially in our simple example, the robot is going to ideally park in front of the table, but not too close. So then we will manually instruct the robot to come even closer and then drop off the block on the table. Okay, so that's how that looks. Here I have a short video of how that process also looks, but I'm going to run this with you right here. Okay, so the first thing we're going to do is just get Gazebo started with the right simulation. So this is from the Baxter Variations package, Baxter on Mobot.launch. And notice that besides from the Kinect sensor, we also have a LiDAR sensor on the mobile base. That LiDAR is going to help us to do SLAM. And for the LiDAR, for the Gazebo plugin, we need GPU in the laptop or something that can emulate it. So take a look at that, or look back at our chapter on LiDAR sensors for more information. So I opened this window, just prepared ahead of time. You'll see we'll have a lot of calls, but here on the bottom, we're going to start the Baxter simulation. Now, here we're not going to do Gazebo Empty World. We have included that into the launch file. And before we run any other commands, you need to remember that this Gazebo simulator needs to complete before we run any other command. Also, you see that as the simulation loads, the red toy block might be on the floor. If that happens, we need to reset the gazebo state. So that command is this one right here, and we've run that command many times, so I hope you're familiar with it. So that helps us to get it back in place. So now that gravity compensation is off, we can continue. The next command is the bundler. Remember that command from last chapter? ROS launch coordinator command bundler.launch. But the difference this time around is that we include another launch file that we're going to be using for mobility, along with 2 navigation services. So, in fact, let me just do a ROS add on it so you can see it. So you can see right here at the end, besides everything that we were running before, we have this Mobot startup navstack.launch file. Okay, so that's the thing that is extra. Along with these 2 services right here, we have the open loop navigation service and the open loop yaw service. This one is used to tell the mobile base to move forward or backwards a particular distance, and this one is used to rotate around its axes for turning around. Oh, let me close it. And for that new launch file, we're going to do a few things. The first one is we need to start what is a map server. This, you can understand it as a server that is holding the latest update of the map, and we need to provide the configuration of that map. It's a YAML file, so this is the way that the map server is run. That's the first thing that we need. The second thing that we're going to need for localization is running this launch file. There's a bunch of other commands being run there that you can take a look by yourself. And then finally, we need to run the move base node, which is going to allow us to do actual navigation. So the package is move base, the node is move base, and we need to include these 5 parameter files, most of which are cost related. So these are some common parameters. This one we'll use for the global map, this one for the local map, and then we'll have local planner parameters and local cost and global cost parameters. It's best to look at the chapters that I mentioned earlier to have a better understanding of what they cover. Oh, this is repeating, sorry. And next, we've started the simulation, we've started these abilities, we want to acquire the block. So let me run this second command and this third command together. We have our simulation here. We're going to run the bundler. So let me just give you a full screen version of that. We have a lot of nodes starting off over here, including moving our arms to a pre-position that is useful for grabbing the block. We've also started, as you can see, the autumn there, all of our mobility nodes. So once we're there, we also have RViz. In RViz, we can visualize the navigation information. So let me show a few things here. The red spheres are coming from the LiDAR. At the beginning, the robot is not properly localized, but that will change in a second. Then this view of the floor and the table here is coming from the Kinect depth sensor. And then all these red arrows is an estimation of the robot, of where it is. So very soon we'll be providing this robot with some goals. The blue color here is the space for avoiding collisions with the environment. So the actual wall is the yellow line, but this is a buffer space that we give the robot to avoid collisions. Okay, so the next thing we want to do is acquire the block. So we can run the acquire block client, action client. And so the robot will attempt a pick of the object. Okay, great. So we go back to our slide. Now we want to do navigation using move base, and as I mentioned before, if we're too close to an object, we might be into a fatal pose. So let's manually move the robot back 1 meter and rotate partially +1 degrees or counterclockwise, just to help it have a good orientation for its navigation. We do that with these two manual raw service calls. Oh, I'm sorry, this is the wrong command. I'll have to fix that. Let me show them to you over here. So this navigation service here is going to send the robot actually 1 meter back. So it's great to see the robot moving. Okay. And then here we have the rotation. All right, so that gives us a better perspective for the robot, and it's going to be ready to move out like this. We can also visualize that in RViz. Let me fix how this looks a little bit, if I can. All right. And in RViz, we also get this scenario. All right. Now we can start navigation to the second table using the action client. We'll move to a via point first and then to the table. So here we're doing a rush run of the action client. This is going to be part of the package example move base client and a node of the same name. So we have that call right here, example move base client, example move base client. So as soon as I do that, you see the green line here in RViz. That is our global path. And then there's a smaller line here that is hard to see. It should be red in color, that is giving us our local path. Now we still have a simplistic example, so the accuracy of the robot as it moves won't be fantastic, but it's following the collision-free navigation path to the table. So here we have crossed our first waypoint. You can see the separation from the wall to avoid any kind of collision. And the robot slowly moves to its destination. In this case, we didn't have to build a map. The map was already formulated. And then there it is, the robot approaching. Sorry, I cannot get a good angle here. There we go. And so the robot then lands squarely in front of the table. Pretty cool. just to see this kind of behavior in our mobile manipulator, similar to what we would see in a robot like the PR2 or Tiago, along with other kinds of robots, maybe with a Ridgeback. And now we're close to the table, but not quite. So we need another manual service call to help the robot move even a little bit further. So we're going to move it 70 centimeters forward and then be able to drop the block off. Okay, so here's that call using the open loop navigation service. And then Baxter will approach a little bit further without colliding the table, and then he will be within reach in order to be able to drop it off. And to drop off, we use the coordinator package with the drop off block client, where it'll find a place, a hard-coded location on the table to put down that block. So that's this last command. And then the robot will get that goal and then execute it, put the block down. Fantastic. So here's an example of a seamless integration of all the different parts of functionality that we've been studying throughout the course. Now, there's still some weaknesses, of course. The drop-off pose is hard-coded, it's imprecise, it's not flexible. So let's now think about how we might address those weaknesses. So within our client, we could potentially combine all of these steps into a single piece of code, along with perception commands for picking up and dropping off the block. That's exactly what we do in the fetch and stack client code that I can show you next, and also give you an overview. So now what we're interested in doing is putting all of this together. Now let's look at a few things over here as an overview. The first thing we want to do with this client is, of course, instantiate all the action servers, all the clients, and all the services that we're interfacing with. The second thing we're going to do is use the action client codes, the action codes, the object codes, to control and manage the entire sequence of actions for the robot. So here for instantiation, just as a quick guide, we're going to instantiate the navigation services. So we see that we have, these are service clients working with this service message and working with these service topics, navigation and yaw. We're also going to instantiate the manipulation task action client. So here we use the simple action client interface with this action message, with this action topic, do the connection. We're also going to instantiate the navigation part of it, which is the move base action client. So here is the action message, the action topic, and we connect. Okay, and by the way, for the move base action client, that's what's connecting to the codes we initiated in our launch file for mobility. That's where the action server has been started. And the last thing we're doing here, oh, this is the same, sorry, that's a repeat, sorry for that. And the second thing we're going to do is control the sequence of actions. So there's a 12-step sequence here. Let me just list it quickly for you. Moving the arms to pre-pose, sending a vision request to find the tabletop, sending a vision request to find the block, send a command to grasp the block, return the arms to a pre-pose position, then move the Baxter backwards 1 meter, rotate the Baxter 90 degrees in the positive yaw direction, navigate to waypoint 1, navigate to the second table, make sure that Baxter is facing in the right direction, so you rotate it and move forward to approach the table closely. Request a vision goal to find the placing pose, and finally place the block on the table. So to run this, we'll need to restart our nodes and run the fetch and stack client, but let's look through the code in this manner for a brief moment. So here we have all our include files for message definitions. We have our global variables that we use in the callbacks. We have some of our goals like global desired flange, pose stamped with respect to torso, and the global object pose and the result. So here we have some of the typical callbacks that we've used before: upon completion, the done callback, feedback callback, the active callback, and also we have a navigate done callback. Okay, so in main, we start defining our goal messages like manipulation task goal. We have our service messages. Here we need some TF move base call, TF listener, and ROS pose, but the TF is the most interesting one, and this is related to navigation, where we'll need to have a frame called map, which will be the fixed global frame. We'll show you how it works in a second. And we have the goal point and the via point. So this is going to be the via pose as a geometry messages, pose stamped. And we have the pose of the table 2 approach. Okay, so here for table 2, the frame ID that we use as reference for the world is map, as I mentioned before. We still need to create that in a second, and we're going to hard code that position with an XYZ, with an XY, and then the orientation using a quaternion. And then we can initialize via pose in the same way, but then change the XY and the ZW quaternion parts like this. The very first thing that we do is instantiate the transform for the map. So here, for example, we have the base link. This is part of the Mobot, and this is where we might think 00 is, but we're going to associate that with map. Now map won't move, so that remains the fixed frame, and this is how we create it. It's not how we create it, but it's how we find this association. We instantiate the navigation services, and we instantiate the manipulation action server right here. After that, we're going to start our sequence of instructions. Now your code is not going to look like this. I have modified it slightly to clean it up. But the sequence is going to be repetitive, and you'll see it over and over again. We'll take our goal message, access the action code element, and set it equal to a desired action. So in this case, we're going to say our goal for the action is move to pre-pose. Once we have done that, we can send the action goal through our variable here, along with the corresponding callbacks. Make sure that this has succeeded. Okay, and then we continue to do the same thing. The next action is to find the table service. That's our action call. We send a goal and then continue. For finding the goal, this is going to be the pose of the block. Let's get a pickup pose for the toy block ID and using PCL vision. So that's part of the action code, the object code, and the perception source. And again, send the goal. Here we just print out information, and then we want to acquire the block or grab the block. So now we do a grab object for the toy block. Send the goal again. Return the arms to pre-pose. Send the goal again. Move the Baxter backwards away from the table. So this is the regular service for the open loop navigation. So the request will access element move distance, send it back 1 meter, and do a client call on that. Here we print that current pose to screen to see for feedback for the user. And then let me see, we're also doing the yaw call that I missed, sorry. And then so here is, we print the information for the navigation, then we do the rotation, and then print that message again. Then we can navigate to the via point at the opening of the alleyway before reaching the second table. So for the move base goal, we access the target pose and set it equal to this hard-coded position we had at the top of our code, and then send it as an action goal. Repeat, but this time with the via point for the second table. So we're waiting for the result, and once that has occurred, we set the target pose here and send the goal here. Only with the navigation callback for this action client. So when that finishes, we'll be close to the table. We want to rotate and move forward. And so here we get our current pose orientation and convert that to a yaw angle that we have here, and then say I want, for the navigation service, I want to take this -90 degrees and subtract my yaw to achieve the robot facing front to the table. And finally, we move forward as well. We get the current pose, and then we use this mathematical equation to find where we are with respect to the table and move forward enough. Oops. For then, let's see that I this is getting a pickup pose, although we're gonna actually fix the arms, place the toy, not pick it up. So this B11, sorry, is get drop off location, and give the toy and PCL vision data, and so this gives us a coordinate that we want to use. That one is saved here in object pose from the global variable result object pose. And finally, we can place the block on the table. So we say I want to drop off as part of my action, and then the frame where I want to drop off is going to be that global variable, but we want to modify the height slightly to place it on top of the table. Okay, and then we send that goal. So this is how the code works. Yep. And so let's see that running. So I come back here to my terminal, and I'll basically kill everything that is running so that my world starts from scratch. We load the gazebo simulation. We wait until that completes before we run the bundler. after we run the bundler, we're going to be ready to run the fetch and stack client. Let me close these windows. Okay, this has finished, so let's run the bundler. Everything is ready to go. And then we can run the fetch and stack client. We begin our fetch. We see our object grasper server doing the job, aligning it properly with the block. Now here we have a little bit of trouble. That block may fall down either during the navigation or at the end when we drop it off. That might be a problem for us. We initiate the navigation calls for rotation. There we drop the block, and unfortunately we do not have any functionality for this kind of error detection right here. So in this case, the Baxter robot will continue doing its full task without any clue whatsoever that it has failed in the task. But you can see all the different elements of how the goal for the navigation was generated there after it reached the first via point. Here it comes. And again, it's just good to see that all of this is running within the client. And as we discussed in our chapter last week, while it's great to see we can do all of these things in the client, that still limits us in terms of flexibility and encapsulation. So I had encouraged you to study the SMASH framework for ROS to be able to separate the control of execution for a robot. And you can learn you can see some nice examples in the ROS by Example Volume 2 textbook that I recommended for, and I will recommend for homework today. Okay, so we reach the table to the right location, and we'll drop off the block, but of course we have no block to drop off. And in fact, because this is still limited, it doesn't realize that this block is exactly at this location. But there we go. We've run this whole thing through the client, and so that's a major milestone. Let's summarize in the next section. Thank you.